Okay, so last section we're going to look at this week is 6.4, which is on graphing all the other trig functions. We're not going to go into as much depth as we did with sine and cosine. Okay. So what we are going to do, though, is use what we know about sine and cosine to figure out the graph of tangent. And the way we can do that, and we just did it in the homework, is let's rewrite tangent in terms of sine and cosine. Can someone remind me again, what's tangent if you write it as a fraction? Chris?
Sine divided by cosine.
It's sine divided by cosine. Okay. So now we're going to focus on the top and the bottom kind of separate, and then we'll kind of put it together and figure out what tangent would look like. So tangent would be 0 when what over here is 0? Yeah? No, not cosine. Yes? Sine. So the only way that a fraction can equal 0 is if the top is 0. So whenever sine is 0, that's when tangent is 0. Well, when is sine 0? Think about your graph. That's what sine looks like. It's 0 here, here, and that's a repeat of the first one. What's the x value of that first point? Yep. 0. How about the x value of the second point? Emily?
0. Or no.
Well, it's over to the right, so it's,
Sorry.
yeah, the y value is
Yeah.
0.
Would that be 1? Or
Well, it's halfway, it's right in the middle of a cycle of sine. So if you know what a full cycle of sine is, it's exactly in the middle. Pi. So that's pi. And then again at 2 pi. So 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Every integer multiple of pi is where sine is 0, which means that's where tangent is also going to be 0. So that's helpful. So now we know the x-intercept for the graph of tangent. But we're also going to have asymptotes. The reason we're going to have asymptotes is because it's a fraction. And what number are you not allowed to divide by ever in a fraction?
0.
0. So there's going to be a vertical asymptote every time that the cosine is 0. So now if we try to think, okay, when is the cosine 0? Well, here's your cosine function. It starts at the top, comes down, hits the bottom, comes back up. It's 0 here and here. That's the quarter mark in the cycle and the 3/4 mark. So what angle in radians is a quarter of the way through the cycle? In degrees it would be 90, but what about in radians?
Pi over 2.
Pi over 2. And what about 3/4 of the way through the cycle? 3 pi over 2. So what's going to end up happening here is with tangent, you're going to get vertical asymptotes at pi over 2, 3 pi over 2, and if you wanted to keep going, 5 pi over 2, 7 pi over 2, 9 pi over 2. It's basically, how can I say it? It's basically pi over 2 times any odd integer. 13 pi over 2, 17 pi over 2, 19 pi over 2. Every multiple of pi over 2 times an odd number. Okay? Where this is every multiple of pi, and that's it. Every multiple of pi. 1 pi, 2 pi, 3 pi, 4 pi. So since we're getting zeros at regular intervals, and we're getting vertical asymptotes at regular intervals, that makes the graph of tangent very predictable. There's going to be a pattern to it, and it's going to look the same over and over. So what we'll do is we'll test some values on each side of these asymptotes and see what we're near. Usually one side is going to be very high, the other side is very low. Okay, so I already copied down my asymptotes. I've got one at pi over 2, 3 pi over 2, and so on. So let me just put a couple of those in. Put one at pi over 2, an asymptote. Let's put one at 3 pi over 2. Now, if I can draw what happens in that green section, that's what's going to continue to happen over and over. So I just, there. Just have to figure out what it looks like in that one section. And what's between those green lines is basically going to be a cycle of tangent. It's going to be one full cycle. If you notice right away, we have an asymptote at 90, we have an asymptote at 270. How far apart are 90 and 270?
180.
180. So you're going to get a full cycle of tangent with a width of just 180. So tangent has a naturally smaller cycle than sine and cosine. It's just how it is. So it's a little bit, naturally, it's just smaller. All right. So let's type this in. Let's do sine divided by cosine. And let's pick a value that's very close to pi over 2. Easiest way to do it is just, let's go pi over 2. Put that in parentheses. And let's just say plus, let's move a very small amount, 0.01. So if you go just to the right of pi over 2, you're going to be way down at negative 100. Way down there. Okay. Now, let's check just to the left of 3 pi over 2. So I'm staying inside these green lines. I'm going to check just to the left. Does anyone have a guess where that one's going to be? Yeah, it's going to end up being at the top. So 3 pi over 2, we'll just minus a really small amount from it. So when you're 1/100th of a unit before the asymptote, you're way, way up. And what about at pi? We say when we're at pi, the value of tangent is what?
0.
0. All of those are at 0. So we're going to go right through that point. So this graph is going to look curved, but it has to go through all those points. So it's going to look something like this. It's going to come up, start to curve, and it wants to keep heading to the right, but it can't. That other green line is going to stop it and kind of force it to just kind of deflect away and curve up. So it's going to go like that. And that's what the graph of tangent looks like. If you wanted to draw a second cycle, you just copy and paste what I have right there. Again, so if I hit graph, you'll see tangent. What you're looking at is the cycle that's right here. It's the first fully positive cycle that you can see. But that's tangent. So cotangent, I'm not going to go through it in as much detail, but it's like everything is flipped. When you look at cotangent, it's cosine over sine. So now, wherever you had an asymptote in tangent, that's going to become a what in cotangent? Yep.
A 0.
A 0. So whatever an asymptote was in tangent, that's going to become a 0 in cotangent. Whatever was a 0 in tangent is going to become a what in cotangent? Oh, Joe?
What was the question?
So a 0 in the tangent function is going to become a what in the cotangent function?
An asymptote?
An asymptote, yes. All the zeros and asymptotes switch places because sine and cosine just flipped. All right. So we can just look at a sketch of that. I already have it. So if you look, pi is an asymptote. Go back to tangent. Pi was a 0. Okay. The other thing, 3 pi over 2, pi over 2. Those were asymptotes. Look at them now. Pi over 2 is now a 0. 3 pi over 2, I didn't draw it, but that would be a 0 as well. And the curve switches, because if you check a point just to the left of the y-axis, which is an asymptote, I'm sorry, just to the right, it's going to be way up. If you check a point just to the left of pi, like if you try 3.13, it's going to be way down. And now, one thing I want to kind of point out, I'm not sure if I put this little box here around 0 on tangent. Yeah, I did. Is we want to look at how many asymptotes we have per period. Well, let's just make it bigger. So when you're looking at one period, you're looking at this right here. What's in that green box? What's pretty clear is the curve itself is in the green box. But what can be a little weird is where are these asymptotes? What period do they belong to? Right? It's kind of like sitting in an auditorium, right? You got two armrests, but if you're sitting next to someone, it's like which, if you're being nice and you're not going to use both, which one kind of belongs to you and which one belongs to the seat next to you? Well, the way you can think of it however you want, but you want to think of it as there's only one asymptote per period. I'm considering 0, the asymptote right here, to be part of that green box. This asymptote is part of the next one, right? It belongs to the next one. So the way I think of it in my head is the one to the left belongs with the cycle. Right? If we go and look at tangent, and I say, okay, here's my graph. Okay, it's the whole, I just didn't draw the whole thing, but I'm looking at the asymptotes. I would say this one at pi over 2 belongs to what's in the green box. The next asymptote would belong to the next green box, which would be right here. Okay, so the main point is there is only one asymptote per period, not 2. Any question on that idea? Yeah, and I think if you think of like armrests where you're sharing them with chairs, that kind of makes sense. There's really only one armrest per chair if you're sharing them. You can't say, well, these two belong to the same chair, because then one chair wouldn't have any. Right? Somebody on each side said, oh, I'm going to take these two, and then 2 seats over, somebody takes those two, the person in the middle wouldn't have any. So that's how you want to think of it, is one asymptote per cycle. At least for tangent and cotangent. So because the period is a little bit shorter, when sine and cosine, you can add 360 to a value, take the trig function, and you get the same answer. Here's an example. So we did this back when we talked about the unit circle. The sine of 500. If I had to do that in my head, that's a big number. I wouldn't want to think of it as 500. I would want to think of it as minus 360, 240, sorry. Why can't I do 500 minus?
It's 140.
It's 140. What am I in, radians? Oh, yeah, I'm in radians. Yeah. So if you do this in degrees, you got to be in the right mode. So sine of 500, there you go. Sine of 140, same thing. You can add or subtract 360 to an argument in a sine function or cosine, and it doesn't change the answer. While with tangent, I could take the tangent of 200, or I could take the tangent of 20. I subtracted one multiple of 180 pi. Right? I could also take the tangent of 380. Anytime you add or subtract 180, it brings you exactly back to the same point, same height, just in a different cycle. So if you go like this, if this was one of your angles you were working with, if you added 180 to it, you would be right here. It's exactly the same height, and that's why you get the same answer. If you subtracted 180, you would be right here. Again, it's the same height, just in a different cycle. That's why you get the same answer. So you can do that with tangent and cotangent. Adding or subtracting any integer multiple of pi, or if you want to think in degrees, any integer multiple of 180 will always give you the same answer. Okay, so you could do like you could add 180 times 1. You could add 180 times 6, 180 times 10. What you can't do is add 180 times 1 1/3. No. It's got to be an integer multiple of 180, or pi. Okay, so any questions on that idea? Okay, towards the end, I got a nice chart that kind of summarizes everything about tangent, cotangent, secant, and cosecant, all in one table. About the asymptotes and how you find like new asymptotes. If you shift it, it kind of makes it very simple. And I'll give you that chart at the end, once we get through everything. All right, so you don't really have to write this part down. I'm just saying that we've done transformations before with non-trig functions. We did them with sine and cosine all week. When you do tangent and cotangent, all the trig transformations are exactly the same. So really quick, we'll just go through and can someone tell me what kind of transformation would A be? Which way would that move the graph? Yeah, Ryan?
Horizontal shift.
Yep, horizontal shift, left or right. If it was plus, it would be left, minus would be right. How about B? What would that do to my graph of tangent? Emily?
Horizontal stretch.
It's your horizontal stretch. Bigger numbers, compress it. Small numbers, stretch it. How about C? Yep.
It's a vertical stretch.
It's a vertical stretch. Bigger numbers make it bigger. Smaller numbers actually make it smaller. And D is a vertical shift. Positive is up, negative is down. So we don't really need to spend a lot of time because it's exactly the same stuff. Rather than having you graph all kinds of different variations of tangent, like shifting and stretching it, I'm going to be interested if you can find mainly where are the asymptotes. Because we know where they are with the original. But what happens if you stretch it or compress it? Well, those asymptotes are all going to change. So where do they go? And that's what the chart at the end will help you figure out. All right. Another thing I'm going to ask you about is what is the period if you stretch or compress or do anything like that? Well, for sine and cosine, you use the formula 2 pi over b. It's the normal period over b. This is really the same formula. It's the normal period over b. Except the normal period for tangent and cotangent isn't 2 pi. It's 1 pi. Tangent and cotangent are kind of the odd ones. They're the only trig functions that have a different period. Sine, cosine, secant, and cosecant are all 2 pi over b. These are the only ones that are different. Okay, so I'm going to just explain how you can find the asymptotes in any trig function. Obviously, it doesn't apply to sine and cosine. There are no asymptotes there. But tangent, cotangent, secant, and cosecant all have asymptotes. We'll look at secant and cosecant next. But the first thing you have to do is find all the asymptotes in one period of the original function. Now, how do you do that? That's where the chart's going to come in. Right? If you can remember, like, oh yeah, pi over 2, there was an asymptote for tangent. Well, that's great if you can remember it. But if you can't, this is what I'm going to give you in a second. Okay. It tells you, for every trig function, where are the original asymptotes? Remember, tangent and cotangent only have one asymptote per cycle. So that's the originals. So these, which we're going to come back to, would help you with this step right here. Find all the asymptotes. You don't even really need to find them. You're going to be able to just look them up in that table once I give that table to you. Right, so step 1, you're going to look them up in that table. And then step 2, this is where you have to do a little arithmetic. You take all the original asymptotes and you set them equal to the argument. Right, so if I had something like tan 2x, that's a horizontal stretch. It's actually a compression. But if I wanted to know what the asymptote would be in this graph, after I shift or stretch or do whatever, I would go to my table, look up the original asymptote, all right, go to tangent, and I'd say, okay, it's pi over 2. So I write down pi over 2. And once I have that, I set that equal to the argument. What's the argument in this case? 2x. And now I solve for x by dividing each side by 2. There's your new asymptote. Now, once you find, how many asymptotes are there in the tangent function? Like if you look at it forever. Or cotangent. Yeah?
Infinite.
Infinite. The asymptotes just keep appearing. The more you zoom out, the more you'll see. How often do you get an asymptote in general? You get one asymptote every what? Yep.
Pi.
Well, it could be pi, but if you stretch or compress it, you're going to be changing the thing that I'm thinking of. But you'll still get one asymptote every period. No matter what the period is, you're going to get one every period. So if you want to write down, in general, what are all the asymptotes, which I will ask you for on the test. What are all the asymptotes in this function? All you have to do is find one of them. Okay, that's what I tried to show you right here. Find one of them, and then add this on the end of it, plus the period times m. Because what you're saying here is you're going to get an asymptote, plus you're going to get one period later, 2 periods later, 3 periods later, 4 periods later. You just have to know what the period is. So you might have an answer like this. I found one asymptote, and then it's going to keep repeating itself every period. Every single period, you're going to get another one. And the period of this one, tangent 2x, is pi over 2. Pi over b. b is 2. That's why I did it like that. So we're going to do another one, but I'm just kind of showing you what an answer would look like. You find one, so that's step 2, and then you put plus the period times m. And that represents every single asymptote you could ever have. Any question on that idea? And if you're saying, well, what about negative asymptotes? What if you go to the left? Well, n could be a negative integer as well. Like if you put in -2, that would give you the asymptote 2 cycles before. If you put in -5, it would bring you back 5 cycles. So that's actually the one we're going to do. So let's find the period of tangent 2x. I kind of already did that. And then we're going to graph it on the calculator showing 3 full periods. Okay. When you're dealing with tangent, what's the formula to find the period?
Tan parentheses x plus n.
So, x plus. Are you thinking of this part?
No.
No? Oh, you're thinking of this.
Yeah.
So this is just basically telling you you can add or subtract 180 to a number and you get the same answer if you're taking the tangent or cotangent. But that's kind of part of the answer. But what is it? Yeah? It's pi over b. To find the period of tangent or cotangent, use the formula pi over b. So in this case, it's pi over, what's b? 2. So that's the first part of what they wanted. And that's important because if I want to find a window that shows 3 full periods, what would be the width of my window if I want to show 3 periods, not just 1? Blake?
3 pi.
That would show 6 periods.
So 3 pi.
3 pi over 2. So you take the length of one period, triple it, and that's what we're going to set our window at. And there's a lot of ways to do it. It's kind of like if I said I want you to show me a window that's 5 units wide. You could go 0 to 5, 1 to 6, 17 to 23, as long as the difference between the max and the min was whatever it should be. Well, this has to be a difference of 3 pi over 2. So the easiest way to do it is 0 and 3 pi over 2. That's definitely a width of 4.71 units. Now, as far as how high and low the graph goes, you don't have to worry too much about with tangent because it's going to go up and down forever. So you're never going to see the top or the bottom. Let's clear that. And you should get exactly 3 cycles. Okay, what's wrong there? Yep.
You're in degrees.
I'm in degrees. So if I wanted to do it in degrees, that's okay, but my window is set up for radians. In degrees, I would change this number to 270. And now it would work perfect. But I don't want to do it in degrees. I do want to put it in radians. So let's put it back to 3 pi over 2. And let's do it in radians. You're going to get the same picture. And what you're looking at is 2 full cycles in the middle connected, and a half and a half. So that's okay. I've kind of cut off a cycle, but you're still looking at 3 cycles. This would be your window. If you didn't want to cut off a cycle, then just slide your window over a little bit. Figure out where this asymptote is, and make that the left edge of your screen. And whatever that number is, just add 4.71 to it, and that'll give you 3 cycles. But again, I'm not really worried about that right now. Hey, how about this one? This one just says to identify which is the graph of 2 tangent x and 5 tangent x. You can assume that the windows are the same in both, because if I change the window, that would change how it looks anyway. The windows are exactly the same. So what are the 2 and the 5 doing? What kind of transformation? Chris?
It's a horizontal stretch.
Yeah, I agree it's a stretch.
It's a vertical stretch.
But it's a vertical stretch. So one of these is stretched vertically more than the other. Which one looks like it's been stretched out more vertically? Yeah, the first one. So that's 5 tangent x. And that's 2 tangent x. So I think as long as you know what the 2 and the 5 are doing, you can kind of figure out which one has been stretched out more. All right, I'm not going to go through as much detail with sine and cosine, but this is what secant and cosecant look like. The reason you get asymptotes is because secant is 1 over cosine. Everywhere that cosine is 0, that's where you're going to get an asymptote. With cosecant, it's the same as 1 over sine. Everywhere that sine is 0, you're going to get an asymptote in cosecant. Now, what I want to focus on is how many asymptotes do you have per cycle? A full cycle is, let me just draw a box. This box in black is a full cycle without cutting off anything in between. A full U shape and a full N shape. Same thing here. This is 1 full cycle. So in those black boxes that I just put, how many asymptotes do you think are in each box? Yeah?
2.
Only 2, right? You can't say that a box has 3 because then one of them would be short in the next cycle. So the way I think of it is the first one and the second one, they belong to what's in that black box. This one belongs to the next box. Okay? You can think of it however you want. It doesn't really matter if you think of it the way I do. Just think of it as there's only 2, whichever 2 you want to think of. It doesn't really matter. So with secant, we remember from graphing it that at 90 and 270, that's when cosine is 0. That's where you get an asymptote. With cosecant, think of the graph of sine in your head, 0 and pi. That's where sine is 0. Well, if you divide by 0, you're going to get an asymptote there instead, 0 and pi. And the way you would figure out that it's a U shape and an N shape, you just have to plot a lot of points. You'd use your table, and I would just maybe do 7 or 8 points. But that's really only what you have to do the first time. Because now that you know what it looks like, if you've got something like this, you've got 3 asymptotes, and you get a point up here, and a point up here, and a point down here, well, you know it's going to be a U shape. And then when I do the next section, I would get a point down here, and one here, and I know that's an N shape. So once you know what you're looking for, it's easier. Now you know. Okay, again, I'm not as interested in you being able to sketch these all by hand. What I really want you to be able to do is figure out the asymptotes. Okay? If you stretch or compress it, where are the new asymptotes? All right. So I think B is always going to be positive, so we're not going to have to worry about that. But if they ask for the period of secant or cosecant, it's the same formula you used yesterday. It's 2 pi over b. So sine, cosine, secant, cosecant. All use the formula 2 pi over b. Tangent, cotangent, pi over b. It's not hard. You just got to remember which one is which. All right. So now this is probably the most helpful thing when you're trying to figure out where the asymptotes end up. So this summarizes everything. It shows you in tangent and cotangent that there is 1 asymptote per cycle. Secant and cosecant shows you there are 2 asymptotes per cycle. Now, why did I pick pi over 2 and why did I pick 0? Well, I just pick the first positive asymptote that I see. Doesn't mean you couldn't pick other ones, but I think if you start picking negative ones, you're going to confuse yourself. So for tangent, your first positive asymptote is at pi over 2. For cotangent, we won't say positive, we'll say our first non-negative asymptote. It's right on the y-axis. For secant, I think to myself, okay, secant, where's the first time that cosine hits 0? That's at pi over 2. What's the next time cosine hits 0? The 3/4 mark in the period, or 3 pi over 2. And then for cosecant, now in my head I'm thinking about sine. What's the first time sine hits 0? It starts at 0. What's the next time it hits 0? Halfway through the cycle at pi. Okay, so what's on the left? Those are your starting points. What's on the right is how you would find the new asymptotes. They all have the same thing on the end, plus the period times n. So you've got to know which formula to use to find the period. 2 pi over b or 1 pi over b. But then all of these, those are the asymptotes in one period of the new function. I'll just put that in parentheses to make it clear if it's not. So those are the first asymptotes in the new one. But how do you get those x1s and x2s? That's what I showed you, right? Here. To find the asymptotes in a trig function, well, step 1 is already done for you. Look it up in the table. You just have to do step 2. Step 2 gives you that. That's what I wrote right there. All right, so step 2 gives you what I just circled. All right, so we'll try a couple examples. But you're going to have one on the test that says something like, here's a secant function. I want to know what the new asymptotes would be. And we'll use the original ones plus this guide on the right to figure it out. Okay, does everyone have that table? All right. So let's start with just the basic secant function. I'm not even going to do any transformations to it. And I'm going to start with the, I'll start with the period. That's probably the easiest one. What's the formula to find the period of a secant function? Yep.
C equals 2, T equals 2 pi over B.
2 pi over B. What's B in this case?
1.
It's just 1. There's just a 1 in front of the x. So the period is just 2 pi. Vertical asymptotes. It's probably using the table. That should be pretty easy. Look at your secant function. What's the 2 asymptotes that they give us in that table for secant? What and what? Oh, Tori? What are the 2 asymptotes they give us for secant?
Pi over 2 and 3 pi over 2.
Pi over 2 and 3 pi over 2. I'm putting those down here because I might have to do a little work with them. Now it says to set the original asymptotes equal to the argument and solve. All right, let's look at the argument. What's the argument in this problem? Chris?
Secant times x.
So there's no multiplication here.
Secant of x.
So secant of x is the whole function, and what's the argument of it? What's the thing you would plug into secant? Like if I had this, remember that's not the log times 2, that's the logarithm of 2. 2 is what I'm taking the log of. So what would you be taking the secant of there? X, yes. So set your asymptotes equal to the argument and solve. Well, since the argument was just x, there's nothing to solve for. This is the original secant. You haven't changed anything. So those stay exactly the same. So I'm going to put pi over 2 and 3 pi over 2. Now, that's great. That's just the first 2 asymptotes, though. You're going to get asymptotes repeating forever. So I have to put plus period times n. This is why I did the period first. What was the period? 2 pi. So you're going to get that asymptote every 2 pi radians, and you're going to get that asymptote every 2 pi radians. 2 different asymptotes repeating every cycle. Okay, now your domain. That's what you're allowed to plug in for x. What are you not allowed to plug in for x? And we kind of already described them. You're not allowed to plug in anything for x that would give you a what?
An asymptote.
An asymptote. That's what you can't plug in. So for the domain, I would just say all reals except ones of that form. So except the ones that would be vertical asymptotes. If you wanted to be specific, you could say all real numbers except any number that looks like this, and then you could write that down. Okay. And now the last thing is the range. How do I type in secant? Because I don't have a secant button. Yep.
1 divided by cosine.
1 divided by cosine. Now I want to know the range. What I'm going to do is I'm going to just going to zoom out a little bit. Does it look like the graph of secant goes up forever?
No.
All right, let me go a little higher then. Let's set this at like -15 and 15.
Yes.
Yeah, it does go up forever. Does it look like it goes down forever?
Yeah.
Yes. The question is, does it hit everything in the middle?
No.
No, there's a gap. So the range has a gap in it. It's everything except what's in the middle. So the way I can figure out what's in the middle is if I calculate a maximum, I can see how high it goes. And they all go exactly the same height. So this goes from -infinity up to -1, including -1. So your range covers every single number from -infinity to -1. Now we said it's going to go up forever. So you're going to have that part. Does anyone have a guess where it's going to have a minimum and then go up forever from there? Yeah. Positive 1, yeah. That's what the range looks like for a secant function. Question on that? I think that's usually the trickiest part. Domain, range, period, those are pretty straightforward. I'm going to skip cosecant x because it's almost the same as secant x. Domain is all reals except the asymptotes. The period is still 2 pi. The range is exactly the same. It's the asymptotes that are different. This part is exactly the same. Only thing that would be different is that and that. So if you do cosecant, that's what would be different. But it's so similar, I want to do something that's a little different. So this just says find the period and the asymptotes. Don't worry about the domain and the range this time. Okay, start with the period. Always start with the period because you need the period to do the asymptotes. Anyone think they can tell me the period here? Yep. Yep. It's 2 pi over 3. All right. And now the asymptotes. What, if you go back and look at your table, what are your original asymptotes for cosecant? There's 2. This and this. Yep.
0 and pi.
0 and pi. I'm not going to put them up there yet because I might have to do a little work. I set each one of those asymptotes equal to the what? Yep. The argument. What's the argument in this case? 3x. So I got a little bit of work to do, but it's not that bad. If I divide each side by 3, 0 divided by 3 gives me 0. So one of the asymptotes is still at 0. Plus the period times n. So technically you could just put 2 pi over 3n. You don't even need to put 0 plus. Right. Next asymptote. Divide by 3. Divide by 3. Your other asymptote is now pi over 3. And And that one is going to keep repeating every 120 degrees. That's what that is. Every 120 degrees, you're going to get another one. Or 2 pi over 3 radians. So there's your asymptotes. I'm not worried about showing a complete graph. That's very similar to what one of the test questions is. Okay, any question on that one? All right. And the last thing is solving equations on the calculator. Very similar to what we did yesterday. The only thing that I'm going to add is this. I don't just want you to tell me one specific answer. I want to know every answer. Okay? So you have to find one and then put the period times n on the end of it. Okay, so with any kind of trig equation, if you can find one solution, then that means there's infinite. Okay? Like if you got this, and you can find one spot that the line crosses it, well, if you continue that line, it's going to keep crossing it. This answer is repeated here, here, and there. This answer is repeated here, here, and here. You're going to get a red answer every cycle. You're going to get a black answer every cycle, over and over forever. So that is how you write your answer. Use your calculator to find one answer. So like find the intersection of the black, where the black dot is, and then put plus the period times n. And then find the intersection for the red dot and put plus period times n. Okay? And you only have to do that if they ask you for all solutions. If they don't ask you for all, you can just do it the way we did yesterday. Second calc intersect, write it down. Second calc intersect, write it down, and you're done. This plus period times n is only if they ask for all. Okay, so we'll finish up with, I've got one example left. Does everyone have that? All right, so this one says all. So already in my head, when I write my answers, I'm going to write down plus something times n, just so I don't forget to do it. Now I'll figure out the rest. Okay, cosecant. I don't have a button for that one. How do I type in cosecant? Yep. 1 over sine of x and negative 1.6. Now, whenever you're solving for all, you just want to look at one cycle on the screen. What's the length of one cycle of cosecant? Yep, 2 pi. If I look beyond that, I'm going to see more answers. I don't care about answers in other cycles. I just want to get the answers in one cycle. So I'm going to see one U shape. I'm going to see one N shape. That's one full cycle. And here are the two answers in that cycle. Second calc intersect. If you're off the screen, just keep pressing the arrow until you come on. 3.82. Plus what Natalie just said, period times n. So the next version of that answer is 6.28 units later. And the next one, 6.28 after that. You could just keep adding 6.28 to that number. Or subtract 6.28. And then we've got one more answer that's separate. So once you get past the halfway point, that should be close enough. 5.61. And that answer will also occur every cycle. Just pay attention, especially if it's a multiple choice question on the test. Are these answers in degrees or radians? If these were degrees, you would not be using 2 pi. What would you use in place of 2 pi? 360. All right. So the homework tonight will be the take home. The entire test is due on 12/14 at, we have a half day. So what time? We're third period tomorrow?
Yeah.
So third period is at 9:15?
Yeah.
So the entire test is due tomorrow at 9:20. Okay. Late equals the sine of 0, which is 0. Any questions on that? So tomorrow in class, instead of taking the second part of the test, we'll review for midterm. I'll give you the midterm review sheet so you can see what's on it, and you can start making your reference sheet. You'll have 39 minutes or so to do that.